Okay, good afternoon, everyone. Let's get started. Sorry for running a little bit late. So, first of all, as you may be aware, the quiz for this week will be available after today's class. So please take some time, like just two, I don't know, single choice, multiple choice problems. I'll give you 20 minutes to finish that. That should be more than sufficient. But don't just open it and doing nothing. Then the answers will just automatically pop up. Then if you ask us to give you another chance to take that won't be fair because you have already seen the answers. Right. So yeah, just to emphasize again, every quiz has some time limit. Right. It has an opening window. Usually is from the end of the Tuesday's class to the midnight of Friday. You can take the quiz at any time during this period, but there is some like time limit. And once you open it, it's just the clock is ticking, right? So just make sure not to miss the exam because you are not aware of the time limit. Okay, but again, we will drop the two lowest grades among all your quizzes. So if you just happen to miss one or two quizzes, that should be fine. Just make sure not to miss the third one. Okay, so let us continue with the random variables, probability distributions, and cumulative distribution functions, right? So we spent quite a while in the last lecture introducing these two types of functions. One is called a probability mass function. So probability mass function is defined as a particular type of probability or the probability of particular type of events. Right? So what are that kind of events of interest? That event is defined by the random variable, right? So we're interested to look at what's the probability for the events defined as x equals to a, right? So mention that this defines a particular type of events, right? So the random variables is a function that maps the elements from sample space to real numbers in a real space, right? So you can imagine you have a sample space which contains all possible outcomes of some like random phenomenon or random experiments you're interested in. Right? So it builds a mapping, right? So it maps maybe your rolling die, maybe some number to other number, or you map we'll say whether you see the snow in the morning or not to 1 or 0, right? So it basically maps all kinds of like random experiments outcomes to a real number, and then we can look into the mapped real numbers and what's the patterns, what's the lemmas, what's insights behind those numbers. So given the definition of the random variables, we can define events, right? So the event described by x equals to a means all the elements in a sample space such that when you evaluate the random variable at this element, the random variable's value is a, right? Does it make sense? Right. So, and then because this is an event, right? This is a random event. It has some probability. So then we index the probability of this event associated with A as the probability mass function value at A. So different A, you can imagine like different A will correspond to different events, right? And those events will have different probabilities. That means the PMF will have different values. That's the definition of the probability mass function. Any questions so far? Okay, so now I just want to a quick check, right? So what does this event definition mean, right? So I can define another type of event. This event is defined as x less than or equal to A. What does this event really mean? Any thought? Let's just do a quick recall here. Yes, exactly, right? So this just represents the event. Remember, event is always a set, right? It's a set of elements in the sample space such that the random variable mapping from omega, the mapped value will be less than or equals to A. That is, the mapped value from a random variable satisfy this inequality, right? That is the definition. So then we define the probability of this type of events as the cumulative distribution function, right? So usually we use a big F, a capital F, to represent the cumulative distribution function, right? Does it make sense? Right? So just be crystal clear. What is probability mass function? What is the cumulative distribution function? They're just the probability of two types of events. Each event type is defined by the random variable. One is defined by the equality, right? One is defined by the inequality. And this probability is indexed by A, right? Remember, the A indexed events. And different A will correspond to different events, which include different set of elements. And this different set of elements will cause different probability value on that, right? So we have the different PMF value and CDF value. Okay. Okay, so why we repeatedly emphasize this, because this is really fundamental for probability theory. And in most literature, you find most content, most topics are discussing about the distribution functions, the probability density functions, mass functions for different types of random variables, right? And in the future, maybe you will be forced to memorize a bunch of PDF or PMFs, right? They're all talking about what does the probability mass functions look like, right? You probably have to memorize some kind of closed form, right? So the first one we would like to discuss is called Bernoulli distribution. Perhaps it's the simplest probability mass function we start with, right? So for the Bernoulli distribution, right? So we're mainly talking about, first we need to talk about the definition of the random variable, right? So we basically assume under the context of Bernoulli distribution, we assume that the sample space will be some kind of binary sample space, meaning that the sample space only contains two elements. Right? So here I will just use flipping a coin as an example. So you only have two outcomes, right? Heads or tails, right? So the sample space will only contain two outcomes, heads and tail. And this random variable will map from each element in a sample space to either 0 or 1. Right? So you can see it's actually binary sample space to two numbers, right? And these numbers usually 0 and 1, but in some literature you might see -1, 1, but they're nothing difference in essence, right? So here the mapping relationship is defined as, in the context of the flipping the coin, we usually define the map from has to 1. And the random variable, when it is evaluated at tails, it is a 0. Right? So this is usually how the random variables under the context of Bernoulli distribution is defined. The sample space is binary. The mapped value is also binary. Okay. And then we define that given this random variable, if we say this random variable x follows the Bernoulli distribution, then the probability mass function has this form. So the probability mass function at 1 is p. The probability mass function at 0 is 1 minus p. And here p is just a number between 0 and 1. Right? So it's actually written here. What this means just means like the probability mass function evaluated at 1 will be some number p. This is a probability. Why? Because p is between 0 and 1, right? And the probability mass function evaluated at 0 will just be 1 minus p. So how about the probability mass function at other choices, at other values of x? It's just 0, right? Because you only have these two maps, right? You map h to 1, you map t to 0, right? For all the other numbers, values of x is just 0, right? So if we write down the probability mass function in a unified way, right? It's usually written something like this. It's written as p to the power of a, 1 minus p to the power of 1 minus a. Right? So this is kind of like a summarize these two formulas. Right? When a equals to 1, meaning that when your random variable's value is 1, the probability mass function is p, right? And when a is 0, that means the random variable function value is 0, right? So you see that p to the power of a will becomes 1 because the power is 0, right? And then the only effective term is this guy, which is 1 minus p to the power of 1 minus 0, which is just 1 minus p. So it actually comes to or is reduced to the second case, right? So I mean, in the future, if you have like in-depth study about probability statistics, you will see this formula repeatedly. Right? It's a very intensive in the literature. Okay, the definition is as follows. If x is a random variable with the aforementioned PMF, then we claim the random variable x follows a Bernoulli distribution, or x is a Bernoulli random variable with parameter p. And shortly, we can write this. We can denote this, use this notation. X, follows This tilde means like follows polynomial distribution with parameter p. Someone asks, okay, how do you choose p? Right? Actually, this represents the family of distributions, meaning that different p will correspond to a different instance of Bernoulli distribution. Right? For example, consider we just flip the coin, right? And you can naturally model the outcome. You can naturally define a random variable x like this, right? You map the heads to 1, you map the tail to 0, and you would like to know what's the probability you see the heads up, which means what's the probability your random variable's value is 1, right? And consider it follows the Bernoulli distribution with parameter p equals to 0.5. What does it mean? What does it mean? You have 0.5 chance to say heads up, right? And that means like you have 0.5 chance to say tails up. It basically means like you are flipping a coin, which is very, which was made very uniformly, right? Like you have the equal chance to say two sides, right? Either side, right? But if p equals to 0.9, that'll be very different, right? That means like, oh, you got 0.9 chance to see heads and only have 0.1 chance to see tail, right? That means maybe you're cheating, right? You're using a specially made coin, right, to win the gambling or whatever, right? So actually, this P indexes different types of Bernoulli distributions, which represents how the chances you see success, right? So usually we view like success probability as P and failure probability as 1 minus P, right? So have a larger success. The larger P means that you have a larger chance to succeed in your random experiment. Any questions so far? Okay, I hope everyone is comfortable with this one because next one will be a bit more complex, but it's completely based on the Bernoulli distribution, right? So it's called binomial distribution. So what is binomial distribution? You can view it as kind of like you want to do a bunch of Bernoulli experiments. By Bernoulli experiments, you can imagine I'm essentially flipping a coin, right? And I'm not interested in only seeing the result for flipping the coins just once, right? I want to flip a coin for 10 times. Then I would like to know how many times I can see the heads, right? If I flip the coin for 1,000 times, I would like to know how many times I can see the heads, right? So this is called the binomial distribution. So the formal definition is as follows. The binomial distribution describes the probabilities for repeated Bernoulli trials, such as flipping a coin 10 times in a row. And the key assumptions here, we assume each trial are independent to each other. The result for one trial has nothing to do with the result for another trial. They're totally independent. Okay? And usually when we describe a binomial distribution, we need to specify two parameters. One is n, indicating how many trials you want to do, right? The other is p, just means what's the probability of success for each trial. Like in the flipping coin as an example, right? So n is just number of times you flip the coin, and the p is just the number for each flipping, what's the chance you see a heads up, right? And then what is random variable, right? the random variable x now is defined as the total number of successes from this n trials, right? Using flipping the coin as example, it's just the total number of heads I'm seeing throughout this n trials. Right? So now I want to review, right? What's the range of the value of x? Yeah, 0 to 10, right? I mean, in general, if this n, then it should be a 0, 1 until n, right? Because you only do n trials, right? That means you can succeed at most n times. You won't be able to succeed for n plus 1 times. You won't, like, you flip the coins, you won't be able, for 10 times, you won't be able to say 11 has for 11 times, right? On the other hand, like, you probably fail to see fail to see the heads throughout this n trials, right? That means x will be 0. But x cannot be negative, right? Because you cannot, like, succeed for -1 times. Okay. Any question regarding the setting here? Okay. So then it is very important to look into the probability mass function for binomial distribution. So if x follows binomial distribution, right, we would like to know what is the probability mass function at every possible value x can pick, right? So that means we need to know what is fx0, fx1 until fxn, right? Okay. How to compute the PMF, right? So to illustrate this, we want to start from like a concrete example, and then want to generalize to the formula, right? So consider a special case like n equals to 5. That means you just do 5 trials, and p equals 0.5. You have a 0.5 chance to succeed, 0.5 chance to fail for each trial, right? So that means for this binomial, for this particular binomial distribution, your random variable x, which is the total number of success, right, will be the range from 0, 1, 2, 3, 4, and 5, right? Everyone is agree at this point, right? And if you want to compute the PMF, we essentially compute fx1, fx0, fx1 until fx5, right? And for each PMF, according to the definition, you're essentially computing the probability of the event defined as x equals to something, right? This something could be 0, 1, 2, 3, 4, 5, right? Does it make sense? Okay. So now let us just pick one particular case. We pick 1, right? X equals to 1, right? So we want to calculate the PMF at 1, which essentially is the probability of the event defined as x equals to 1, right? So now the question reduced to how do we compute this the probability of this event, right? So the question is, how do we represent the event defined as x equals to 1? Mm-hmm. Mm-hmm. Mhm. 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 Yeah, I mean your idea is exactly is totally correct, but we want to like start from concrete examples and then reduce to the general formula. Yeah. So let's just look into this event x equals to 1, right? So to figure out what exactly this event means, right? We need to first figure out what is the sample space, right? So now I want to ask, what's the sample space? Is this sample space still, I mean, here we still want to use like flipping the coin as example, right? So now I flip the coin for 5 times. Right? Is the sample space still binary, like only including T and H? I guess not, right? And what should be appropriate definition of sample space? Any thought? Yes, right? So you are talking about, you actually um, have given us the correct answer about the sample size, the space of the sample space, right? The size of sample space. But here, we want to first clarify that now you are throwing the coin for 5 times, right? Each time you're going to say a side, right? And suppose in the first time you say the side head, right? And the second time you say the side tail. Third time you might say head again. And first time you say tail. And last time you say head again, right? This sequence of the size you're saying throughout these 5 uh, trials actually form your outcome, right? It's not just one side, right? You actually will see 5 sides correspond to the results after 5 trials, right? So actually every outcome in your sample space should be represented by a sequence of like 5 results, right? Either heads or tails. Does it make sense, right? So that's the difference between the binomial distribution and Bernoulli distribution. Bernoulli distribution, you just you just throw the coin for flip the coin for once, right? You only see heads up or tails up. You only see one side. But now binomial means that okay, you're gonna throw the flip the coin for many times, right? Every time you will see one side. Now you have to put all the results into one sequence to represent what's the final outcome after you finish this trials, all those trials, right? Any question? Okay, then more formally, we should represent the sample space as a sequence of 5 binary results, right? Because here we just take n as 5, right? Meaning that you toss a coin, you flip the coin for 5 times, right? So the sequence, each sequence should be should contain 5 binary outcomes, right? So then the sample space includes all combination of 5 possible size you have seen through the trials, right? So that's maybe I should use like uh result 1, result 2, result 3, result 4, result 5 to represent the result for each trial, right? And each trial, here I'm using RG to index R1 through R5, is either has head or tail, right? So then, of course, this is 1, J is between 1 and the 5, right? So this set actually contains all possible combinations of the 5 trials results, right? So you see each result, say R1, you have two possible sides, right? Heads or tail. R1, you have two. R2, you have two. R3, you have two. R4, you have two. R5, you have two. So in total, you have 2 to the power of 5 possible different sequences, right? These 2 to the power of 5 sequences form the whole sample space. Does it make sense? Right? I hope everyone is on the same page, right? Okay, so now things becomes clear, right? Remember our x, the random variable defined under binomial distribution, is the total number of heads you have seen, right? So now let us look at the event defined as x equals to 1, meaning that the number of the total heads is just 1. In this event, which sequence outcomes should be included? If I choose one, let's just list every possible sequence should be included in this event, right? This event is defined as, okay, x equals to 1, meaning that the total number of heads through our 5 trials is just 1, right? And then, of course, this event is a set, right? This set must contain a bunch of elements in the sample space. Each element in the sample space is just a sequence, right? So now, can we enumerate every sequence in this event? Any suggestion? Right. In other words, which sequence in this sample space indicates that you only have one path? Yes, exactly right. You just look into enumerate all the sequences, right? And pick up the ones who only have one has in the sequence. All the others are tails, right? This sequence means that, okay, you only have one has. Right? If we enumerate, these are just the first sequence, the first result is has, and all the other are tails, right? Or the first is tail, second is head, all the other are tails. Or the first, second are tails, third one is head, and remaining are tails. Or first 3 tails, fourth head, and last one tail. Or all first 4 are tails, last one is head. Right? Is there any other sequence like not listed here? No, right? Because these are all sequences that only contains one head, right? There won't be any other sequences also containing one head, right? Because the only one head can appear either in the first result, second result, third result, fourth result, fifth result, right? It can appear in other places, right? We only have 5 trials. Okay, does it make sense? Right? Okay, so the next question is how do we compute the probability of this event? In other words, how do we compute the probability of this set, right? Then we just need to look at sequence by sequence, right? So so first, what is the probability of the first sequence in this event, which is H, T, 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 T. What's that? Yeah, that's a that's a good, but but let's consider like in general case you got P, right? You got the parameter P, right? Let's consider the definition of binomial distribution, meaning that you're gonna independently flip the coin for 5 times. Then when you observe this sequence, what's the probability of this sequence? Yes, right? That's the definition, right? We just flip coin for independently. That means like whether you say heads or tails has nothing to do with other trials, right? So you can see in the first trial, you say heads, right? Then the probability you see the heads in the first trial is just a P, right? And in the probability, the next trial, you say the probability you say tail is what? Is 1 minus P, right? So it's 1 minus P. And third trial, you see tails again. Again, it's independent to other trials. So the probability is still 1 minus P. And fourth, 1 minus P. The last one is 1 minus P. So if you write it down, it's just P, 1 minus P to the power of 4, right? Does it make sense? Right? And then you got the probability for seeing one sequence, right? So how about the probability of seeing the second sequence? It's the same. Why? Because if you look at, if you really want to multiply this together, you will see the first one is 1 minus P, right? Second one is P. Third one is 1 minus P. Fourth one 1 minus P. Last one is 1 minus P, right? If you multiply it all together, it's still P times 1 minus P to the power of 4. Why? Because you only see one head, we can only have one factor of P, and you have 4 tails. So why? That's why you're gonna multiply 1 minus P for 4 times. That gives you 1 minus P to 4, right? So similarly, you can just look at all the other sequences included in this event. You see that because every sequence, you only see one head and all the other tails. So the probability you see that sequence is always P, 1 minus P to the power of 4. Does it make sense? Right? And that means like, okay, if you write down all those probabilities together, they're actually the same. It's P to the power 1, 1 minus P to the power of 5 minus 1. 5 means the number of trials we did, right? Does it make sense? And then added them together, we get our probability of the events that including all the 5 sequences, right? So which is just 5 times P to the power 1, 1 minus P to the power of 4. Does it make sense? Any questions so far? Okay, so now let us extend this case, right? Let us consider x equals to 2, right? X equal to 2, English means like we flip the coin for 5 times and we observe 2 heads, right? And we want to compute the mass function at 2, meaning that we want to compute the probability of the event defined as x equals to 2, right? So the question is, we need to first define, we need to first figure out what does it mean for x equals to 2. In other words, what kind of sequences, outcomes do we have in this event? What? Yeah, I'm not asking the total number of sequences. I'm asking like, what does the sequences look like inside this event? Yeah. Set of 5 outcomes for 20 that include exactly 2 points. Yeah, you want to supplement? Yes, yes, yeah. You're all. I mean, the answers are all great. So basically meaning the same thing. So basically, you can imagine like you enumerate all 5 possible sequences, right? You just look at all the sequences which you have 2 heads. All the 3 are tails. Actually, there are quite many. There are quite a few such sequences, right? If you just write a few, right? So it could be has, tail, right? It could be has, tail, has, tail, right? It could be has, tail, and has. Or it could be tail, has, tail. You name it, right? You just enumerate every sequence. Question? Yes, yes. That's the things we're about to discuss, right? So here we just want to give everyone a concrete sense, like what does it mean, right? X equals 2, what does it mean? It actually includes many sequences, right? Um, so you name it, you can enumerate. The last one I believe will be like the first 3 are tails and last 2 are heads, right? Then the question would be, okay, how do we compute the probability of this event, the probability of this set, right? Okay, let's stop. Let's rest for 5 minutes and then continue. Okay. So let's continue. So now we know that x equal to 2 represent events that contains all the sequences in the sample space that contain 2 heads and 3 tails, right? And of course, depending where these 2 heads show up, so you have quite many sequences, right? So the first question is that for any of those sequences inside the event, what's the probability for one sequence? Say, this is one example of the sequence, right? I got 2 heads in the first and second trial and 3 tails in all the remaining trials, right? So what's the probability of observing this particular sequence? Yes, exactly right. So, I mean, just according to the definition, the probability you see the head in the first trial is P, and probability you see the head in second trial is P, and the probability you see the tail in the third trial, 1 minus P. Remember, every trial is independent to each other, right? So the first one, 1 minus P. The last one, you see the tail, the probability is 1 minus P, right? They're independent, so the probability, their joint probability is just multiplying all those factors together, which gives P to the power of 2, 1 minus P to the power of 5 minus 2, right? Which is 3, right? And similarly, for another sequence, right? Although this sequence and the second sequence and the first sequence are not the same, right? They actually are totally different outcomes. But the probability of observing such a sequence is still P to 2 times 1 minus P to 3, right? Because they are independent, right? As long as you say one sequence after some trial, one head after some trial, you're gonna have some factor of P, right? And for the remaining tails, right, you're gonna have factor of 1 minus P, right? So in total, the probability is P to the power of 2, 1 minus P to the power of 5 minus 2, right? So the probability of our event, right, of our event, for the whole event, x equals to 2, will be the probability of the summation of the probability of each single sequence, right? And the probability of each single sequence is the same. They are all like P to the 2, 1 minus P to the power of 3, right? Then the summation is just multiplying this probability of each sequence by the number of sequences in the event, right? So then how many sequences are in the event? Some of you have pointed out. It's 10, right? It actually can be more formally written as 5 choose 2, right? So everybody knows this concept, right? 5 choose 2 means that, okay, I'm gonna, from 5 items, I can random pick up, not random, I pick up 2. How many possible ways I'm gonna pick up 2 items? It's 5 choose 2, and it's just 10. Right? Then that means my probability of x equals to 2 is just 5 choose 2 times P to the power 1 minus P to the power of 5 minus 2, right? So any questions so far? Hope everyone is super comfortable at this point. Okay, now let's generalize to N and K, right? So in general, we talk about binomial distribution. You do N trials, and you want to look at the total number of successes, right? In other words, in the context of Filipino core, the total number of heads, right? So if you want to look at x equals to k, right, means that I want to look at how many sequences which contain k heads in the sample space, right? So then we need to compute n choose k, right? In the previous case, we just want to leverage n5 choose 2, right? So in general, we want to compute n choose k. Right? How do we compute n choose k? Yes, exactly, right? Thanks for memorizing this formula. I don't need to explain anymore. So basically, we just leverage this formula, right? So n choose k can be computed by the factorial of n divided by the factorial k divided by the factorial of n minus k, right? As to why this comes from here, I believe everyone knows that, right? And if it's not, I just give you like, you can imagine you just choose from n items, k items, choose k items out of n items, right? But there's no concern about in which order you're going to choose those stuff. That's why you have to divide k factorial and n minus k factorial. It's just to divide all possible orders of those k items and also the remaining items, right? So then overall, we can derive the probability mass function for the binomial distribution. So the PMF at k, which essentially is the probability of the event defined as x equals to k, is computed as the probability of the single sequence in that event times the total number of sequences in that event, right? The total number of sequences is computed by this n choose k, right? Because we want to say among all n trials, which sequences contains only k successes or heads, right? So the total number can be computed by n choose k. The formula is here, right? And then for every sequence, no matter at which positions you see the heads, right? The probability of a single sequence is always p to the power of k and 1 minus p to the power of n minus k. Why? Because those trials are independent to each other, right? As long as you see one has, you can you're gonna have a factor of p in your joint probability, right? I'm saying k has, then you have multiplication of k factors of p, right? And all the remaining are failures or tails. You got n minus k failures, so their probability will be 1 minus p times 1 minus p times 1 minus p until like n minus k times. So they will give you 1 minus p to the power of n minus k. So this gives us the probability mass function. Any question regarding this? Okay, I hope this formula doesn't look too complex to us, right? So there's one interesting observation, right? So we know that the PMF represents the probability of the event defined as the random variable takes value 0, 1, 2 to n, right? So then if we add them together, right? What's the value should this be? I heard that. Can I speak more loudly? Why is 1? Yes, exactly, right? So this just represents the probability of x equals to 0 plus the probability of x equals to 1 plus plus the probability of x equals to n, right? So actually, actually, if you look at those events all together, right? Those events first, they are mutually exclusive, right? Their pairwise disjoint, and the union of those events form the whole universal set, right? The sample space. Because the random variables, the total number of the successes must either be 0, 1, 2, 3, or n, right? So if you unify them together, it is a deterministic event, right? It must, this whole event must happen, right? So that means the summation of all those probability must be 1, right? Does it make sense? Okay, so then if you look at the formula here, right? If you look at this binomial distribution, the PMF here, you'll find that the left-hand side is written things like this. So you sum from k equals to 0 to n, and each summand is n choose k, p to the power of k, 1 minus p to n minus k, right? This is 1, right? So what does this look like? What's this? I bet everyone has seen this before, maybe in primary school, right? This is actually, if you expand a polynomial, p plus 1 minus p to the power of n. This is how you expand these polynomials. If you take out all, if you want to expand these polynomials and decompose it as a summation of polynomials at different orders, this is how you're gonna have the decomposition. Right? And you see that this guy, p plus 1 minus p, is what? It's just 1, right? 1 to a power of n is just 1. Does it make sense? Everyone's happy with this? Right? So this corresponds to general formula, right? So if you look at this x plus y to the power of n, right? If you expand this form, right? You have a summation like this. Sorry, n to k from 0 to n, and you got n choose k, you got x to the power of k, 1 minus, sorry, it's not 1 minus, x to the power of k, y to the power of n minus k. Okay. If you expand this power to the some summation to some power, right? And then it will be decomposed as a summation of all those polynomials, right, at different orders. Right? It's a very well-known lemma. Now you can see that it actually coincides with the binomial distribution PMF you found here. An interesting coincidence. Okay. So binomial distribution might be a little bit complex, right? They will want to introduce even simpler distribution. It's called geometric distribution. So what is geometric distribution? It defines a particular type of the event that the first k minus 1 trials are failures. Only the kth trial is the first success. Okay. So here the random variable x is defined as the first time you see a success. Going back to the flipping the coin example, right? That basically means like if I flip the coin for 10 times, from which time is my first observation of the head? It might be, I may observe my first head at the first time, right? Or until the 5th time. Right? So obviously, The even defined as x equals to k is just one sequence, right? It's just all the tails for the first k minus 1 times. And then with heads in the case time, right? And then what's the probability, or what's the PMF at k? The PMF is just the probability of observing this sequence, right? All the first k minus 1 trials, you say failure, or tail, right? Until the last time you say, until the case time you say success or head, right? So the probability is simply 1 minus p to the power of k minus 1, and then times p, right? So if the random variable x has such a PMF, then we say x follows the geometric distribution, and its PMF is like this, right? Okay. So now we can do some like simple practice, right? So what's the probability? Suppose you try something, right? You flip the coin, you do some gambling, right? For many times, right? And what's the probability you lose for the first 3 times and winning for the fourth try? Can anyone give me a formula? Yes, exactly, right? So you lose for the first time, first 3 times, like meaning that in the first 3 times, all you see is head, is tails, right? It's toss a coin, right? And until the fourth time, you see the head. So the probability will simply be 1 minus p to the power of 3. And in the fourth trial, you see the heads, you succeed, right? The probability is p, right? So that's the probability. So you see that because the event defined by the random variable value only contains a single event, right? It is always like fail until the last one is success, right? So you only need to compute the probability for a single event. There's no other sequences contain this event. That's why you have this probability. You don't need to consider a constant factor in front of it. Right? That's the big difference from the binomial distribution, right? Because for each event you find a binomial distribution, you might contain many sequences. Okay. So now let us review our Monty Hall problem, right? So we previously discussed, right? When we play the Monty Hall game, right? If we switch the doors, we got 1/3 chance of winning, and sorry, 2/3 chance of winning, right? Only have 1/3 chance of losing, right? So that's why we should switch the gate, right? When the host is showing you some gold under gate 3, right? So now suppose we play the game for 4 times. What's the probability of winning exactly once? So here we're assuming like you playing the each Monty Hall game is played independent, right? Has nothing to do. The results are not influencing each other, right? Mm-hmm. Mm-hmm. Okay. So first, what is P? What's the value of P in our case? What? 2/3, right? So you got 2/3 chance. Here we always choose to switch the doors, right? So you got 2/3 chance of winning. So P is equal to 2/3, right? Of course, 1 minus P will be 1/3, right? So you play the game 4 times and you win the game for once, right? This is like a binomial distribution, right? You got N equals to 4, you got P equals to 203, right? So you want to say the winning for exactly for once, right? That means you want to calculate the PMF function at 1, right? Remember, X, the random variable under the binomial distribution, represents the total number of successes, right? Right? So the PMF at S1 is the probability of X equals to 1, which according to our formula, you have to first calculate 4 choose 1, right? And choose K, right? 4 choose 1, then times P to the power of 1 minus P to the power of 3, right? So that's the, if you look at this, is 4 times 2/3 times 1/3 to the power of 3, right? It's a little bit I mean, tedious to compute this, but this is how we compute that, right? Then how about you winning 0 times? All 4 times you just lose. One over 3 to the 4th. And yeah, that's correct answer, right? But we should match this to the formula, right? So if we just apply the formula first, so here K equals to 0, right? N choose K means 4 choose 0, right? 4 choose 0 is just 1. Right? This guy is 1. You can calculate, you can verify by yourself, right? And then P to the power of number of success, which is 0, right? 1 minus P to the power of 4 minus 0, which is 1/3 to the power of 4, right? Okay, so we want to do one more practice, like what's the probability you win 3 times? Yes, exactly, right? You just apply the formula. N choose K now becomes N 4 choose 3, right? And the number of success 3, that means like P to the power of 3, 1 minus P to the power of 4 minus 3, which is 1. And that's it. Okay, let's stop here today and see you on Thursday.